Hello, this is Jack Jackson. In this video, we're going to get into what I think is probably maybe the very heart of a high school or college geometry class, and that's talking about triangle correspondence and congruence. So most of our work this week and next week, or this playlist and next playlist, will center on the concept of a triangle congruence. Now, later on, we're going to give a more general definition of congruence in terms of transformations so that we can think of any two geometric figures in a plane as being congruent if and only if they can be moved to exactly coincide with each other with some combination of translation, rotation, and reflections. And this really works best in Euclidean geometry. In order to continue our study in unified geometry, however, we're going to recall that we've already defined what's meant by congruence of line segments and angles being equal measures. Uh, and we can use these definitions to define what is meant by congruence of triangles. So triangles are congruent if and only if there's a bijection from one or the other so that corresponding sides and angles are congruent. Okay, so here's our actual definition for a triangle correspondence. A triangle correspondence is a continuous one-to-one correspondence bijective function, in other words, one-to-one and onto, both injective and surjective, between two triangles or triangle in itself such that vertices correspond to vertices and sides correspond to sides. So we're mapping vertices to vertices, sides to sides in sort of a natural way. Okay, and these will preserve betweenness relationships as well. The continuous part sort of guarantees that. So what do we mean by that? We mean by that if basically, if something is between 2 points in the original triangle, their images will be between the 2 points there and the other one. So mainly just got to keep track of where the vertices go. So given a one-to-one correspondence between triangles or a triangle in itself, the correspondence is a triangle congruence if and only if vertices correspond to vertices, sides correspond to congruent sides, and interior angles correspond to congruent interior angles. So two triangles are then congruent triangles if and only if there exists a congruence between the two triangles. And we use this notation here, triangle ABC is congruent to triangle A prime, B prime, C prime, to indicate a congruence where A corresponds to A prime, B to B prime, and C to C prime. So that all six corresponding parts of congruent triangles are congruent. Sometimes you'll see that abbreviated CPCTC, corresponding parts of congruent triangles are congruent. So by that we mean that AB line segment is congruent to line segment A prime B prime. So those two sides are congruent. Line segment BC is congruent to line segment B prime C prime. Those are congruent. And the final pair of sides, corresponding sides, side CA is congruent to side C prime A prime. Those are congruent line segments, so equal lengths. And then we get the same thing for the angles. Angle BAC is congruent to angle B prime A prime C prime. Angle ABC is congruent to angle A prime B prime C prime, and angle ACB is congruent to angle A prime C prime B prime. Notice when we use the symbol congruent here, when we're talking about the geometric figures, we could have expressed the same relationship basically by saying AB equals A prime B prime with no marking on top, because then we're talking about the lengths of the sides. Or we could have said the measure of angle AB of BAC is equal to the measure of angle B prime A prime C prime, because then we're talking about the numbers, the measures. Now, when you see this, we're going to read this as triangle ABC is congruent to triangle A prime B prime C prime, but we really mean more than just to say they're congruent. It's stronger than when we use this symbol like this, is stronger than just to say that they're congruent. We're saying they're congruent by a specific congruence, that A and A prime match up, B and B prime match up, C and C match up, C and C prime match up. So angle A is congruent to angle A prime, angle B is congruent to B prime, angle C is congruent to angle C prime, and sides AB are congruent to side A prime, B prime, and so forth. So we get all six of these things happening. That's what we have. Okay, So we're talking about a specific congruence. So this little thing here will help with the definition of congruent triangles. And it gives sort of both definitions here, the transformation version and then the version that we're using right here where we have congruent parts. Okay, and one of these, okay, so this one looks like this one here. Here's an example, and this one is congruent to it here. And so is this one down here. If you move one, you move the other. So if you look, all the corresponding parts are congruent. I kind of labeled them in a kind of convenient way to help keep track of it. A prime, and A double prime are congruent angles. Right at the moment, they're measuring 13.98 degrees and so forth. And you can see the same thing for the sides there. So all the sides and angles are matching up. Going back to the notes, you see a static picture of that thing that we just looked at. Here's a link to an earlier video. Some of these things, my earlier videos use things that I did in Geometry Sketchpad, which is almost completely defunct now because it's not supported anymore. You can't really buy it anymore. But I'm gonna leave these up on my website, my YouTube channel anyway, if you want to watch those old things. But I'm trying to replace all these videos. Now, here's the thing I want to talk about. Now that we defined what we mean by congruent triangles, well, it turns out that congruent triangles, just like congruent line segments, congruent angles, is equivalence relation. And so congruence of triangles is an equivalence relation. So it forms equivalence classes where all the triangles that are congruent to each other, triangles congruent to self, and every other one in that class, but it's not congruent to the ones in another class. So we have a couple of related major questions. So the definition requires that we get 6 things congruent, right? All 3 pairs of corresponding angles have to be congruent. All 3 pairs of corresponding sides have to be congruent. That's the definition. Okay, so if we go by the definition, we have to find all 6 of those things and show it. Here's the question. Can we get by with less than that? Okay. In other words, can we get by with less if we know maybe, what if we know 5 or 4 or 3 or 2 or one of the parts is congruent, one corresponding pair? Is that going to be enough to say that you get all 6 corresponding parts congruent and the 2 triangles are congruent? So here we go. What if we know that 5 of the pairs of corresponding parts are congruent? Can we conclude that the remaining pair of parts are also congruent and thus the triangle is congruent? Well, for Euclidean geometry, the answer is yes. Does it matter which 5 corresponding parts we know are congruent? No. In Euclidean geometry, it doesn't really matter which 5 you pick. As long as they're corresponding and they're congruent, you'll get the 6th one for free. Well, okay, but not 5. How about 4? What if we know that 4 pair of corresponding parts are congruent? Can we conclude that the remaining pair of parts are also congruent? Again, for Euclidean geometry, the answer is yes, and it doesn't really matter which ones we look at. What if we know, I'm not saying that's the case for the other geometries that we're looking at. We'll have to look at those later. What if we know that 3 pairs of corresponding parts are congruent? Can we conclude the remaining pairs are congruent? And this is really the key question, because in Euclidean geometry, it depends on which 3 you have. Okay, sometimes the answer is yes, sometimes it's no. So this is, I think, just right at the heart of a study of geometry is answering this question. What if we only know 1 or 2 parts of the corresponding parts that are congruent? That's never enough to conclude the 2 triangles are congruent. So we're going to ultimately explore these and answer these questions for Euclidean, taxicab, hyperbolic, and spherical geometries. And it turns out that solving this question for 3 corresponding pairs of congruent parts being given or established is the critical question. Through our investigations, we will show that knowing only 1 or 2 of the 6 pairs of corresponding parts are congruent is never enough to determine that the 2 triangles are congruent, regardless of the geometry. We'll also determine that knowing 4, 5, or 6 pairs of corresponding parts are congruent is always enough to determine the two triangles are congruent, and Euclidean geometry, maybe or maybe not in the other geometries. Well, that's to be determined by our investigations. So the key questions are the following. Suppose we're given 3 of the 6 congruencies between corresponding parts of two triangles, or a triangle itself. Is it enough to determine if the triangles are congruent? In other words, can we get the other 3 corresponding pairs of parts congruent for free? Do we have like a buy 3, get 3 free sale? Okay. Okay. There are 6 cases to consider. The bulk of this week's informal study will be looking at all these cases. And there's several possibilities, what we call side angle side, side side side, angle side angle, angle angle side, angle angle angle, and side side angle. Those are the different combinations and orders of pairs of corresponding parts where we know 3 of them are congruent. And we're going to examine these in Euclidean, taxicab, hyperbolic, and spherical geometries. First, starting with Euclidean geometry, which we would do in a high school geometry class. So if you're a high school student reading this, watching this video, then you would do exactly this, and you may or may not get to the other geometries. Now, even this question, there's actually 2 perspectives here. Sort of 2 ways to look at this problem in two scenarios. The first one I'm going to call measurement conditions, and the second congruence conditions. So in the measurement conditions, what if we're given specific measures? Like we're given, we know that a triangle has sides of length 2 centimeters, 3 centimeters, 4 centimeters. So that's a side, side, side condition, measurement condition. We know the specific measurements. The question is, number 1, can you even build a triangle with those sides lengths? And if so, are they all congruent? Well, if you can't build it with that, then there's 0 triangles possible, 0 congruence classes of triangles that work with that. On the other hand, if maybe all of them are congruent. Well, if that's the case, then there's 1 congruence class. In other words, there might be different triangles. There might be one on my piece of paper or your piece of paper, but if they have the same measurements, we should be able to basically pick mine up, put it on top of yours. We might have to flip it over, rotate it, scoot it over some, but we can set it on top of yours and it would match perfectly. That would be congruent. If that's the case, those are in the same congruence class. How many congruence classes are there? Maybe there's 2. Maybe there's 3. Maybe there's infinitely many. So we have to determine that. Okay, that's our big question. Okay, how many different congruence classes are possible for a specific set of measurements, or in general, how many different classes can you get with a certain measurement condition, like side, side, side. The other one, so there we're given a measurement and we're trying to determine how many congruence classes. The other one is we're given 2 triangles. We're told some given corresponding parts of congruence without specifying their measurements, right? We know, for example, that all the corresponding sides are congruent. That's the side, side, side congruence condition, but we don't know the actual measurements of the side and we don't really care. Do the 2 triangles then have to be congruent? In other words, do we know that all the corresponding angles have to be congruent in that case? So in each case, there are homework set tasks in my class exploring each condition in each of the 4 geometries within unified geometry. And it might turn out that the conclusions we reach depend on the geometry. We're going to put off proofs and formal investigations until our next playlist next week, or next chapter in my notes next week, in my class next playlist in this on my YouTube channel. Well, there are 6 here are the 6 possible triangle correspondence conditions where we know the 2 triangles exist and they have the indicated 3 pairs of corresponding parts congruent. Question then, is this enough to determine the remaining 3 pairs of corresponding parts are congruent and thus the triangles are congruent? We will have to determine the answer is yes or no for each of these conditions, for each of the geometries. At this point, we've not established the answers to these questions at all. Furthermore, the answers might be different in the different geometries, and we'll have to investigate this week. So here are the conditions. So you know what I mean when I say these. Side angle side condition, congruence condition, or corresponding condition. We say the pair of triangles, or a triangle with itself, had the side angle side condition if the 2 triangles are in correspondence so that two pair of corresponding sides are congruent and the pair of corresponding angles included by these sides are congruent. So this angle is between those two sides. Side, side, side condition, we say the pair of triangles or triangle itself have the SSS condition or side, side, side condition if and only if two triangles are in correspondence so that all three pairs of corresponding sides are congruent. ASA condition, we say a pair of triangles or a triangle itself have the ASA condition if the two triangles are in correspondence so the two pairs of corresponding angles are congruent and the pair of corresponding sides included by these angles are congruent. Notice angle, angle, side, and angle, side, angle both have two angles and a side that are corresponding congruent, but the order is different. So the angle, side, angle, you start at an angle, go around to the side next to it, then the angle next to that. You can be going clockwise or counterclockwise. This one you have an angle, angle, and side. So notice that this side is between these two angles here, included in both angles. Whereas this one, the first angle, is opposite that side. So for the angle, angle, side, we say that the pair of triangles or triangle itself will have an angle, angle, side condition if and only if the two triangles are in a correspondence. So the two pairs of corresponding angles are congruent and the pair of corresponding sides opposite one of the pair of corresponding congruent angles are congruent. Again, the first angle and that side are congruent. If we've said this as side, angle, angle, it's the same thing, but the standard way is to say angle, angle, side. The SSA condition could also be ASS condition, but we write it this way, probably for obvious reasons. And we say that a pair of triangles or triangle itself have the SSA condition or side-side angle condition if and only if the two triangles are in a correspondence so that two pairs of corresponding sides are congruent and the pair of corresponding angles opposite one of the pair of corresponding congruent sides are also congruent. So that first side is opposite that last angle. And the last one is the angle, angle, angle condition. We say a pair of triangles or a triangle in itself have the angle, angle, angle condition if and only if two triangles are in a correspondence so that all three pairs of corresponding angles are congruent. And our big question then is in each of these 1, 2, 3, 4, 5, 6, 7, 8 conditions for each of our four geometries that we're going to be looking at, is that enough to say that you get the other parts, corresponding parts congruent, and thus the whole triangles are congruent? It's important that we're talking about corresponding part of another triangle, and we're talking about comparing, could be a triangle to itself, but usually we're talking about one triangle to another triangle. We're not talking about, say, two sides within a triangle being congruent to themselves. We're talking about a side of one being congruent to a side in another one, for example, or same thing for angles. Again, congruence of triangles is an equivalence relation. Thus, congruence partitions the set of all triangles into congruence classes, so that all the triangles within one class are congruent to each other, including congruent to themselves. And for specific measurement conditions, we won't know how many classes are formed. And we have the same conditions. Side angle side measurements, we use a length 1 angle measure and a length 2 to indicate the measures of two sides of the triangle and measure the included angle. For example, we could talk about a 2 centimeter, 1.3 radian, 5.6 centimeter triangle, or a 3 centimeter, 45 degree, 4 centimeter triangle. For side, side, side measurements, we use length 1, length 2, length 3 to indicate the measure of all three sides, like a 2 centimeter, 4 centimeter, 5 centimeter triangle. ASA measurements, that's angle measure 1, side length 1, angle measure 2. For example, 2 radian, 5 centimeter, 0.3 radian triangle. The 5 centimeter side will be there, and on each end of it, you'll have those two angles. Angle, angle side, we, again, angle measure 1, angle measure 2, length. So, for example, a 2 radian, 0.3 radian, 5 centimeter triangle is the angle, angle side. Notice that the 5 centimeter side will be opposite the angle that has a 2 radian measure. In this one, we have a pair of opposite ones here. The first side and the last angle there, the only angle, those are opposite each other. So, for example, this one is 5.6 centimeters, 2 centimeters, 1.3 radians. This 2 centimeters next to the radian, 1.3 radian angle, but that 1.3 radian angle is opposite the 5.6 centimeters. And then, of course, we just do the three angles for the angle, angle, angle. And the question is, number one, is there even a triangle that will work for these conditions? If there is, how many different? So if there's not, then there's just 0 congruence classes. If it does work that you can make one and they're all the same, that's 1 congruence class. If you can make it 2 different ones, but that's it, that would be 2 congruence classes. Maybe there's 3 congruence classes. Maybe there's infinitely many congruence classes. That's what we're going to have to try to decide. Okay. So let me go ahead and give you a task here to work on. And I think this is a really good task to work on here. So what I want you to do is get some unlined paper, get you a compass, a ruler, and a protractor. I'm using a pro-radian protractor for these, but if you don't like the, just change these to degrees, these radians, and use a degree protractor if you don't have a radian protractor. Okay, but see if you can work these out. So I've given you a condition. What you want to do is see if you can make this thing. If it's impossible to make it, you should have a drawing that kind of shows it's impossible and then say so. If it is possible, then in your process of making it, did you determine that no matter what was going to happen, it was going to be congruent? Well, if so, then you're 1 congruence class. If you can make 2 different triangles with these measurements that are really different, that the other measurements don't match up as congruent, then maybe you have 2 congruence classes or maybe even more than that. Okay? And so here what I've got is several things here. And so we've got a couple of side angle sides. We got a couple of angle side angles, a couple of angle sides. We got 3 on the side, 4 of the side angles, and 3 of the angle angles. So see if you can work these out. Like I said, if you only have a degree protractor, just convert these radian measures to degrees by multiplying by 180 divided by pi, and then see if you can work this out. The order matters. For example, 3, 4, and 5 are different. Okay. So 3, 5, and 6. So let's look at 3. 1.5 radian, 4 centimeter, 0.5 radian. Okay. 5 is 1.5 radian, 0.5 radian, and 4 centimeters. It's the same numbers, right? But this one down here is angle side, number 5. So this 1.5 radian needs to be opposite the 4 centimeters. Whereas this one up here, you draw the 4 centimeters in the middle, and these 2 angles are on both ends of that line segment. Okay, and then like number 6, this one is the same numbers again, but this time the 0.5 radians is the one that's opposite the 4. So there's 3 different orders there for those, 2 of them in the angle side, 1 the angle side angle condition with the same numbers, but they're going to be different triangles. Okay, so see if you can work that out. So after you do this, see if you can determine, this is in Euclidean geometry, how many different equivalence classes are possible for each of these 6 congruence conditions or measurements conditions, and then maybe we can solve this question, and then also maybe answer the same question for Euclidean geometry for the conditions for congruence as well. So try these yourself, and when you've spent some time with this, see if you can discover what's going on your own here.